there we are. We're ready to go. Good. I shall start on the hour. Well.
Give me a warning, then I can start recording.
Oh, okay, right. You have a 2-minute warning.
And I take it you will keep to 45 minutes plus discussion.
I'll do my best. I'll try and leave some good time at the end for some questions.
Yes. I'm sure there will be many questions.
Looking forward to it.
Well, I can't be sure because people may be fading by now. But, okay. What does my Lord say? You have exactly 1 minute, according to my Samsung.
Yeah, I've got the same here on my clock as well. So yeah, good.
Okay.
Good.
So we are in tune.
Let's see if this is about the right height.
Oh, if you want to see it, that me is me. So.
Hello, Barbara. Barbara, I should say, I'd like to say thank you very much because I know how hard and how much work goes into this kind of thing. Herding physicists is not just like herding cats, it's like herding Schrödinger cats.
No, it's like pushing the wheelbarrow full of frogs.
Absolutely. Yeah, you're right. So,
okay.
I know what
okay, John, we assume that everybody is there and they can also join if they are a little bit late. So,
okay.
Over
Ready to go. Right, well, this...
Recording in progress.
Good evening, everybody. This talk's going to be about looking at quantum mechanics from a sub-quantum level, and quantization is going to be brought in roughly halfway through the talk. So for the first part of the talk, I'm going to look at something which underlies quantum mechanics. It's not going to start with quantum mechanics, but so I need to allow this to be recorded.
You cannot. I'm recording.
Okay, but I've lost my ability to clear my screen.
Oh?
Yes, just a minute. I've lost my ability to move out, or it says the meeting's being recorded, got it, but I don't have a mouse. Oh, wait a minute. So I can't get to...
That's, I have enabled multiple participants, so that's the only thing I can do for you.
Okay, just a minute. I need to...
Oh, it's moved.
Yes, good. I've got it now. Right. Good. Okay. Right. We're back in business. Okay. So this talks about subquantum mechanics, but it's entitled subquantum chemistry, because the new theory which Martin and I developed over 30 years is a development of Maxwell's electromagnetism, but also a development of relativistic quantum mechanics. Now, that quantum mechanics is one that is apt to be used, that can be used for thinking into the nature of quantum reality more clearly than can things that have gone before it. I want to try and show how that is, but then also to start using it, to start to take the next steps beyond the physics to thinking about what that means for, first of all, chemistry. That's going to be the main subject of this talk, but of course what's coming next is solid-state physics, and then the development of materials and devices and systems from using the kind of thinking that's made available by this new way of looking at reality. So the picture which you see in front of you is a dielectron, is a diagram of a dielectron boson. I'm going to come back to that, and it's a mixture of dielectron boson is a combination between a spin-up and a spin-down electron. These things are all over the place in chemistry. This is the kind of thing that in the helium atom is that perfect round spherical shell, which is totally spinless, chargeless, magnetic fieldless, diamagnetic, something which excludes even a magnetic field, of the perfect and beautiful helium atom. So that's the picture we're looking at just here at the moment. Now, before we start, some acknowledgements, and I've got special thanks for a couple of people from NASA, Brian Druin and Michael Mercury, for this talk. For the last few months, we've been meeting once a week, and Brian's a chemist, and Michael's an engineer, and but I'd also like to acknowledge a couple of other people that don't perhaps know they need, a few other people that perhaps don't need to know they should be acknowledged. That's Peter, Lou, Garnet, Mike, Inez, and Viv, who are also acknowledged below, because they've had some influence on the thinking which has gone into this as well over the course of the last year or so. But a special thanks really are to my colleague and good friend, it's no longer with us, Martin van der Mark, with whose collaboration a lot of this work was developed. So we're going to look at the relativistic quantum mechanics of chemistry. So what one would expect is to just use Dirac quantum mechanics. That is the relativistic quantum mechanics of the standard model, but I'm not going to do that. And the reason I'm not going to do that is that it's not adequate to the task. Now, what's the evidence that it's not adequate to the task? Well, Dirac quantum mechanics is 90 roughly years old, but nobody uses it for this kind of thing. There's a reason for that. The Dirac theory is very, very beautiful, but it's too complex. The solutions to it are too abstract, or too mathematical to be used as brain tools for thinking into these things. And it doesn't seem to fit the reality of what one observes in nature in a way that's useful for thinking and engineering, or thinking about physics or engineering new devices. Instead of that, I'm going to use the Williamson-van der Mark theory, which is shown at the top here on the right as an equation. And that's a development of Maxwell electromagnetism that includes mass, rest mass field, but also includes, on the one hand, spin, on the other hand, current, vector potential, kind of something that's related to a current. This theory is simpler, and I think it's even more beautiful. The equation is more beautiful. I think the problem with Dirac, where Dirac goes part the mist in, goes the mist in, goes into the mist, and makes things difficult to see, is the quantum mechanics problem, the general quantum mechanics problem. So I've got Schrodinger's hat here, and the basic problem with Schrodinger, or with Dirac, is that one can see clearly only half of the time, because as something rotates, one gets into a situation where one doesn't really know what's happening. It's gone into imaginary state, and then it does something, and then it comes back once again. And that system where one has something which is uncertain, where one doesn't know certain things as an axiom, is one that makes it difficult to see beyond a certain point. And the whole thrust of the work that Martin and I did over 30 years was to get to a system where one can think clearly about the underlying things that lead to quantization. So I'm going to talk pre-quantization and then show where or try and show where the quantization comes from, and then give some examples from chemistry. I'm not going to do as much chemistry as I would perhaps like, simply because of time constraints. But Arnie and I are now working on, I think, 5 papers simultaneously that have to do with this thing. I'll pull in a little bit here and there from those. This is really based on the first of those papers, which talks about the basis. So the other thing about Dirac quantum mechanics is that the mass that appears there, ID/-m, it's really a lump of mass. It's a mass which is put in there just as an object which is needed because the system is massive. It's not part of the dynamics of. So it's not a direct part of the dynamics of the Dirac equation. That's part of the problem. The other thing is that the psi there is a spinor psi. It's in a set of objects which are in a spinor basis. Now, that's required, and it's required that the solutions to both Dirac and Williamson-van der Mark equations are spinor solutions. But this one, but in the Dirac case, they obscure them. One doesn't think in terms of real physical quantities, like the field and the spin and the current. One has to think in this more abstract space of spinors, because that's what it works in. And also that complex imaginary that appears in the ID/, it's too simple. It's it's an imaginary two-dimensional space. It's not non-commutative. It doesn't act like reality. You've put something in there, you've forced your thinking into a narrow space where things are stuck in flatland, and you're not properly able to think into three-dimensional or four-dimensional reality. So what do? Well, if you switch to d mu psi mu nu, that d mu is a four-vector derivative that's designed to be the basis of inverse space and inverse time. I'll come on to say more about what I mean by inverse space and inverse time as opposed to space and time in just a moment. But that thing encapsulates a division, which is a division of something by a little bit of space or a little bit of time. Now, it has to do that. It has to do that separately because the algebra that we're talking about here, a Dirac algebra or any relativistic algebra, is not a division algebra. And yet I'm going to use divisions. So I need to choose those divisions to be somewhere where they're unitary. In most of the space, they're not unitary. In fact, and you can see this very simply, the interval between two events, the invariant interval, on the light cone, dx squared plus dy squared plus dz squared minus dt squared, goes to 0 on the light cone. And if one divides that, if one does a d by d tour on the light cone, one doesn't get an infinitesimal, one gets something which is both infinitesimal, but dividing by something small, you get something very, very large. You get an infinity. In fact, you get any number between 0 and infinity. This doesn't act like a normal differential. And actually, that's just what you want, because the probability of having an interaction far away and long ago is then very much magnified by the fact that this detour brings you much closer, in the way that light brings you closer to the rest of the universe too. So, although it sounds undesirable mathematically, it's perhaps desirable physically that things have such a property. However, to describe dynamics, we need to sit in a position where we can understand what's going on, and that has to be unitary. We have to think about processes and also physical processes must conserve energy. They must be unitary. And that is the case for the separate division of d by dt, d by dx, d by dy, and d by dz. Each one is a unitary operator. It turns out that the subset of the equation on the top right, d mu psi g is going to be a 16 component, 16 linearly independent objects, not a 2 as in complex space. So it looks much more complex, but I hope to show you that complexity is something that we're actually used to. Those 16 are things we know about, as you'll see. The subset of that, where you just look at the psi mu nu's, at the bivector part of it, precisely parallels Maxwell's equations. So just as Lou was describing in the first talk, if you properly put in the vector as being a vector potential, then the derivatives of that give you the Maxwell's equations, the field equations that was first derived by Weil, as he also said at that stage. So this new formalism brings in the 4 free space Maxwell's equations in their totality, whereas the Dirac equation doesn't. One has to bring it in as something which modifies a phase of a supposed wave function, a one-dimensional object, in terms of a connection with the vector potential times charge. EA is the way you bring that in the Lagrangian for the Dirac-Lagrangian. Technically, don't want to go too far into the maths in this thing though. So the new quantum theory, therefore, because it's more in tune with reality, with the reality of fields and spin, allows thinking into things that are in a completely new kind of way. One gets a much deeper insight into how stuff fits together in these different spaces. And that's the hope. The hope is this new thinking leads to new materials, devices, and engineering. So we'll start by moving from relativistic quantum mechanics into chemistry. But before we do that, I want to talk about space and time and inverse space and time. And we need to go beyond the just energy approach of either the Hamiltonian or Lagrangian formalism. So this is, in a sense, taking a step back to the 19th century and saying we're just going to derive the equations of motion and work with that. How? Well, by trying to do something which is precisely the way that nature works. Then a solution of Hilbert's 6th problem, one could say. That's an attempt to do that. It isn't there yet, but it's trying to take a step which becomes closer to that. We need something that's going to be both fully relativistic, so not the Schrödinger equation then, and properly quantized. And we need to quantize the things that are quantized in reality if this is an algebra reality. So charge and spin amongst 2 well, amongst other things, but they're perhaps the most important. Now, the Maxwell base is a good place to start because it was always fully relativistic. It was fully relativistic at the point Einstein was born. So it was fully relativistic in the 19th century, and it remains fully relativistic now. It's the same thing. And hence the proper light thinking, the cartoon that was shown earlier of Einstein riding along on a light beam. But the Maxwell theory is not complete because it doesn't say anything about quantum spin. Actually, it doesn't say anything about charge as well. One puts that in by hand, charge and current. Now, there's another thing about the way that Maxwell developed his thinking. He developed it in quaternions. His thinking was in terms of quaternions, not in terms of vector calculus, which hadn't really been invented yet. That was the Gibbs-Heaviside thing invented later. And he acquiesced with teaching in that kind of formalism because thinking in quaternions was thought too difficult for students. And given that the students then became professors, generations have since been teaching our students to not think properly. And thinking in quaternions, as I'm sure Peter will agree with, takes you a lot further to understanding how stuff works. And I'm going to show in this how quaternions absolutely click through the algebra. The space-time algebra is riddled with quaternions. They're a subalgebra of the Clifford algebra CL13, and they appear in kind of copies within that algebra. I'll show how that works. Now, the 90-year-old Dirac theory did introduce spin, but it was too obscure a way to actually think in spin space. Spin space seems very mysterious. Oh, the spin could only be up or down, but up isn't up and down isn't down. It's some sort of, and then somebody says SU2 in some group theory thing, where there's some imaginary space, which is, it's just bullshit. You can't do anything with that. You're stuck in something which is, what can you say about it? Well, you only have a mouthful of teeth. There's nothing you can say because you're stuck in something where you don't really understand what this space is in which that spin exists. Within that formalism, one needs a formalism which tells you what the nature of quantum spin is and allows you to calculate it, and then allows you to think in it, to go back to developing, thinking about the materials and devices you might like to do. So the result is that if you take a quantum chemistry textbook, I've got one sitting here somewhere, and look at it, the only game in such town is H psi is E psi. It's exclusively Schrödinger. Dirac's just not used. It's not there. It's also not there in solid state physics. It's not there in most of physics. It's only there in people who look at Dirac per se, really. Now, Dirac, Maxwell, and Schrödinger are all good in little windows. They all do very well. If you want to bring everything together, one has to do better. We need a proper theory to enable spin thinking, the ability to think in spin. So, right, to start on that, I just want to talk first of all about space-time and inverse space-time. If I take a space and I make a Artesian space, or if I make a polar space, thinking about concentric spheres, then that space is an extensive space in which I can measure distances. I can say how far apart two things are in that space. I want to invert that space, and also I have space-time. I have an Einsteinian space-time, which is already inherent in Maxwell. If I think in time, I have something which is an ordered sequence of events where you can look at differences between the sequence of events. That thing moves in one direction, where space you can move either way. So it's a different kind of dimension. But nonetheless, one has some extensive space and some ordered time. But if one looks at their inverses, put simply, the inverse of time is frequency. The inverse of time is music. It's a pure note. It's a frequency. It's a delta function in that system. If you want to think about something which is a photon which has a particular color, it may have a particular note that's associated with that. We're thinking about something which is musical in this inverse space. And yet that inverse space is in the same direction in terms of the vector direction of space-time algebra. Now, there's a paper out June of this year, which Martin and I worked on for many years, which talks about how the inversion leads through to invariance. All the important invariants of physics appear as divisors in this inversion, and also how that relates to interaction, how things interact with one another. Because if you have some complex distribution, a 16-dimensional space with some stuff in it, energy, and you want to transfer it to some other thing that might be 16-dimensional, they need to be inverses of one another in some sense. because a thing times its inverse is the number one, is the unit. It's not quite the same as the number one as in one thing, as in one universe, but it's a scalar unity that exists within these algebras, which exists within the complex algebra, the Quaternion algebra, this algebra. But that thing should be, one should realize that is a distinct thing from the number one representing one universe. But there is an inversion where you can find an inverse to any, you can find an inverse to many vectors. This is not a division algebra, so there are areas where division is not defined, but looking at where they're not defined means one that can then understand where you can use them in a vector algebra. And that's a paper that was published June 2021, reference up there. So what is inverse time? Inverse time is frequency. Inverse time is that dimension in which quantization happens. E is h nu, A is h times the frequency. It is the space of quantization, it's the space of discrete objects, of pure notes then. Characteristic energy is in some senses an inverse time. Of course, I know the dimension is different between energy and inverse, and energy and inverse time, but it is frequency where one does quantization. So, and spatial frequency too, the spatial frequency is the momentum. It's related to the momentum, again, through the same constant, through Planck's constant. The dynamics of interaction require inverses. To get the thing, a lump of energy from A to B, has to have a system which is up to an amount, and that amount is the amount of energy transferred, an inverse of each other. Now, the thing is that if we do differential dynamics in this new theory, in this d mu psi g, chi g equals 0, then one ends up with a set of spaces that are distinct and are separate, and yet are connected to one another. And these spaces are not 4 spaces, they are 3 spaces. But those 3 spaces can be associated with 1 spaces. So an example of a 3 space is just space, x, y, z. And an associated dimension you might think is t, time, x, y, z, t, for dimensionality. But it turns out that as you put these things together, one can associate the 3s with a set of different ones to form 4 spaces, or effective 4-dimensional spaces, that have different properties. The most important of those new spaces is the Quaternion space. Quaternion space is x, y, y, z, z, t. So it's things that are products of x times y, they're bivectors, they're areas, with the scalar. Now, that particular part of the space-time algebra is isomorphic to quaternions, and it's also the generator of rotations for all the other spaces. They all rotate in the same way, which is essentially, if you've got an object described by this, if you rotate something, you don't want one bit of the rotation to go one way and the other bit to go another way. They've all got to rotate together, and they do. So the quaternions are absolutely central to this as well, and they're a different set of 4 objects to space and time per se. Trying to show how that works by just... Now, I don't want to do too much maths in this. I've been through the maths of this stuff in previous talks, but some maths is essential. I'm going to show the maths and then try and explain what it means. So here's a showing of the maths. We're going to do a 4-vector differential. That's this object just here, it's a 4-vector differential. So it's d by dx mu, d by dx, d by dt, d by t, minus d by dx, minus d by dy, minus d by dz. That's what this thing says. It's a 4-vector differential. But if you look at the details of this, it also contains a division of the base elements. So it's got a 1 over, so a differential is a special kind of division. So it's 1 over a bit of time plus something, 1 over a bit of space, plus 1 over a bit of space perpendicular to that, plus 1 over a bit of space in the z direction, or r theta phi direction. It's a 4 derivative, but it contains the unit elements. And absolute relativity, which I'm going to use in this, means that I'm not going to allow anything to happen which doesn't contain its proper unit element. So I'm going to bake the fundamentals of relativistic space-time into the mathematics. So
John, excuse me. Are those 2 equal signs correct, or do you want to be adding those 2 things to the rest of it?
No, the 2 equal signs are correct.
So then this d by dx mu with an inverted alpha is equal to these other d's, which are right. Which have non-inverted alpha.
The partial inverse is this d mu. Actually, probably I should describe that u as being a superscript there if you wanted to look at covariant and contravariant. but because those are subsumed in the algebra, I don't need to do that here. So if I'd done that properly, I would probably have done d sub mu if I wanted to look at cone contravariant. Is that what you meant? This d mu is d by dx mu. It's that part of it.
You have an inverted mu here, alpha here, and you have non-inverted alphas in the next line.
Yes, I do, and that's because the inversion of alpha 0 is alpha 0, precisely, and the inversion of alpha I, of alpha x, alpha y, alpha z, is minus alpha I, alpha x, and alpha z. So alpha I equals minus alpha I is 1 over, just as it's 1 over I, and I squared is minus 1, gives the same thing. And because the metric is plus minus minus minus, that gives the sign change. Okay? So yes, they are correct. Right, so that's a 4-vector derivative acting on a 16-component object. That 16-component object is 4 1 spaces and 4 3 spaces, which are about to be described. And they're written here as this is psi or chi qi. This is chi g, a general chi, a general thing that can carry information, carry energy, but it's a root energy because we're going to have to form a square. These things are at the level of a wave function, rather than at the level of a probability density. So we're sitting sub-quantum mechanics here, once again. And here are the components. So psi p is the scalar component of the zero-dimensional part. Psi 0 is the time component of the 4-vector. Psi 1 is the x component, if you like, or the r component, r theta phi component. So 1, 2, 3 here are a 3 set, x, y, z, r theta phi. Any conformal orthonormal coordinate system has the same detailed properties at the intensive level. So 1, 2, 3 stand for a 3-dimensional algebra. So this bit here, alpha 0, alpha 1, alpha 2, alpha 3, is time, space, space, space. And everything else follows from that in terms of them being divisions of a bit of something divided by a bit of something else, as in that vector differential of this object. So that's the maths. And if I just miss out all of this and just take these objects, this line here, the psi 01, psi 02, psi 03, those first three are going to turn out to be, if I make the psi 1, if I make this not a space, but a vector potential, so or a 4-vector potential, in fact, so that would be the charge, and this is the current, or is related to the charge and the current through the normal mechanisms in Maxwell's equation, in the way that Maxwell described Maxwell's equations originally, anyway. Then these objects are the electric field, and this 3 is the 3 components of the magnetic field. An electric and magnetic field so the electromagnetic field has 6 components: antisymmetric, tensor in the normal formalism, and electric and magnetic mix between each other. So one is electric, is another frame's magnetic a little bit, and they mix in the way they should, and that's easy to show. So what we have is, if we just take the 4 differential of the 6 components of the electromagnetic field, we just get exactly all 4 Maxwell's equations. So that bit is just Maxwell's equations, and it's just going to reproduce Maxwell's equations exactly because that's what it is. It does it in one step, so it's nicer than a tensor formalism or nicer than introducing an epsilon ijk, but it just does it in a step. So the new theory encompasses Maxwell, but it has these other components as well, these spin current components. So what does that look like if we do the whole thing? I need to speed up a bit because I'm taking too much time on the maths and not enough time on the thinking. The d psi UG looks complicated. It's got a lot of components, but it reduces to the terms on the right. The first 4 of which are Maxwell's equations plus a derivative of mass, a time derivative of mass, a mass flow, in place of where you'd normally put the charge. So what it's doing is it's saying that the charge is really an energy exchange. So what it's doing is saying the charge in Maxwell is really the same as the energy exchange in quantum electrodynamics. So as you want, as you need to have for making that correspondence between the 2 theories that describe electromagnetism in human understanding at the moment. And there's a similar divergence for the similar gradient for the quadravector, but that appears to be 0 most physical systems. But apart from the first 4 equations, one now has 4 more coupled equations, a set of 8 coupled differential equations, which describe, first of those is just the gauge. It's just the standard gauge. Look at it. It's just divergence of A plus dA by dt. It's the Lorentz gauge if it's set to 0. Just the gauge equation. So, hey, that's brilliant. That's a supplementary equation that one normally wants to get some sort of solutions in Maxwell, which is under constraint. And that's the one used. The radiator is the one used for photons. If you set it to something other than 0, then you get, if you set it, you can set 3 differential to 0, then you get the Coulomb gauge, and you can look at systems that have a 3-dimensional symmetry. So the fact that the right-hand side is equal to 0 is not necessary. It's just the simplest case where you have an isolated particle that's not interacting. But look, the last equation looks like a gauge equation too, but it's a gauge equation of spin, because that T is a spin density. It's a quantum spin density pre-quantization. So it's going to be quantized, because it has to be quantized, because, well, we'll come to that. So the mass field and vector spin things both constrain the physics. Any solution has to be a solution of both the first set of 4 and the second set of 4, which is normal. Normally you take the first of those, the 5th one, the Lorentz gauge, and impose that as well as the Maxwell's equations to narrow down your solutions to something that's more like the physical solutions. So this is the kind of thing you want. But the central bit of these, the other 2 equations, equations 6 and 7 here, are equations that relate curls of current to spins, and spins to curl, and curls of spins to currents. So they're like Maxwell's equations, but they're between the odd parts of this algebra, the current and the spin, and not the even parts, the fields and the masses. So that's what they are. So that's the maths of it. And I really want to get out of maths. So what I'm going to do is, instead of doing maths, I'm going to have a look at these things. Now, what this table is due to my ex-student Ines Anderson Morrison. And what they are is they're a description of what you get when you divide a little bit of something on the top by a little bit of something down the left-hand side. So let's just make that bigger, because if I can, actually, just see if I can. Yeah, I can make it bigger here. Good. So I just want to look at, so instead of looking at the mass, I'm going to look at this picture. So what you have down the diagonal is anything multiplied by itself is just the scalar. So the diagonal here is the scalar coloured yellow. That's the pivot. That's the rest mass part of it. Transforms. It's invariant under a Lorentz transformation. Now across the top here we have the 4 vector, which of course varies in the normal way with the Lorentz transformation. It's defined to do so. It's constructed to do so. It's the space-time algebra. It's the Clifford algebra 1-3, which has been largely taken forward by Hessenes since 1980 or so. So these red objects are just the 4 vector, but they form combinatorics. They form combinatorics that form 4 single elements. These are single elements here in the corners: yellow, grey, and these 4 here, and these 2 here, because they're repeated. And these 2 here are the single elements: 1, 2, 3, 0, 1, 2, 3. This is what I call the hedgehog, because it's a directed volume element, and this is the quedgehog, because it's a quantum hedgehog or a 4-dimensional hedgehog, a directed element that can be either outward directed or inward directed in space-time. This is just a scalar mass, and this is time. So time is also singular. But then if I look at space, and I look at the product or the quotients, because I'm dividing something that has this form by that form, obviously dividing x by x, dx by dx, I just get something which is a scalar. But if I do dx dy, or dy dx equivalently, these things are really, when I was multiplying x by y, I'd be getting an area. So what I'm doing here is I'm getting also an area, because 1 over one of these space-time elements is either plus or minus the same space-time element. So this thing doesn't have signs in it. All of this stuff is antisymmetric. So if something has a plus sign here, has a minus sign here across this diagonal, because of the non-commutativity of the whole algebra, which Lou explained beautifully in the first talk as well, why that's the case. It has to do with what a differential is. That non-commutativity runs through this whole table. But this thing here, they're the quaternions. That square there are the 4 quaternions. This is 1, that's x, y, and z. Or x hat, y hat, z hat, which are rotations about x, rotation about y, notation about Z. And the effect of multiplying one of those things with anything on this table, so if I've got something which is defined as being in the X direction in some way, that could be just the X direction, or it could be EX, or it could be BX, or it could be spin in X. If I hit it with one of these things, it'll rotate it through 90 degrees into Y. If I hit it in the opposite order, it'll rotate it through 90 degrees into minus Y. So these are the quaternions. They are a sub-algebra within this algebra. And they are a basic algebra for all of these other sets. Well, there are actually only 4 of them. So this, and this are the 4 3 spaces that I was talking about. What are they? Well, this is the quaternion one. That corresponds to magnetic field, it turns out. This is the electric field. This is X, Y, Z. So this is the normal things, or R, theta, phi. And this is spin. So the ones down the other diagonal of the spin, set of 3 spins, spin around X, spin around Y, spin around Z. And those things are entirely not in X, because the spin around X is something which is a spin, which is d by dt of a circulation in the xy plane. So it's like an axial vector, but then doubled. It's defined, the spin in Z, just like the magnetic field in Z, is really in the xy plane. It's really a product of, or a quotient of something, of a bit of something in X divided by a bit of something in Y. That's taken as being conventionally the Z direction, like a vector algebra. With spin, the same sort of thing happens. And these things are the 4 3 spaces. Now, this is lovely for humans. Why is it lovely for humans? Because we're good at 3 spaces. And what I've done is I've taken something which is nastily complicated at 4-dimensional basis, put divisions into that, divide a bit of stuff by another bit of stuff, and I've ended up with a bunch of 3 spaces. And humans are good at thinking in 3 spaces. So the question is, what are those 3 spaces, and can I use them for thinking into matter, into chemistry, as it's going to be shortly? So let's see how we can do that kind of thing. So any questions at this stage? Because I've gone very quickly through some pretty nasty maths, and I've got only 10 minutes left, so I've taken longer than I should have done. So perhaps I better just press on. Okay, let me press on and say how this sort of thing works. Let's just shrink this down so it can be seen. Actually, let's play it again. Okay, so what those relativistic processes look like is they look like, actually I won't do that here because I've got a mouse. This is one of the single spaces, that's a single space, that's a single space, and of course time is a single space. And the Williamson-van der Mark equations give relationships between them. They're linear differential equation relations in a normal kind of way. Some of these you know about because they're just Maxwell's. So for example, the curl of the vector potential is the magnetic field, as you would expect, up to a sign. And this thing is a curly thing. These arrows denote d by dt, and the solid arrows denote either div or grad, depending whether they're going up a grade or down a grade. So here you've got starting scalar, vector 1 index, bivector 2 indices, trivector 3 indices, pseudoscalar 4 indices, and also the multiplicity of these spaces. There's just one scalar. There are 4 vectors. There are 4 trivectors. There's 1 pseudoscalar, and there are 6 field vectors. So one's going up or down, depending on, and that's what these colors mean. So you're going from a 6 field down to a 6 object down to a 4 object, that's an orange arrow. Going from a 4 up to a 6, that's a blue arrow. And if we're looking at solutions to Maxwell's equations, they flow around this psi jk to psi I to psi I0 to psi 0 jk. Magnetic, vector potential, electric field, spin. Now, Maxwell's equations don't talk about these two, and in fact, these connections were missing. Hence, Maxwell's equations always were incomplete. One always does solutions of Maxwell's equations at the second differential level for that reason. But this is the photon loop. There are other possible loops, but this is something which can support a photon wave function. We can look at this same thing again, but then looked at in a different way to try and give an analogy of what these things are. Don't take these two literally. But this thing is really a root rest mass energy. This is time frequency energy. So if you think about it in the fabric of space-time, it's like a linear deformation. If you imagine space-time being a matrix, you push it in the vector direction. It deforms along that direction and perhaps contracts perpendicular to that direction a bit. This one's like a torsion. The magnetic field is really like a torsion. you're twisting the thing, putting something into it like that. And the electric field is like a space-time twist. It's a twist in space-time. You can do that because you have space-time plane. You just twist it a bit in space-time. A bit harder to imagine, but nonetheless. But this one's the important one. This is the one that's been missing. This is the spin term. That's a tide vortex. Something which is dx by dt, which is like a velocity or a momentum, that is then about some lever arm. So it's the circulating momentum, but it's a constrained circulating momentum. What's it constrained by? Well, it's constrained by being attached to all these other things. These are not independent objects. What's happening is, to get from magnetic field to spin, magnetic field is two-dimensional. You kind of unfold it and open it out. You open it out in the time direction, so you fold it out in time. All of these relationships are either an infolding or an enfolding, an outfolding of one dimensionality to another one through a differential thing, which is really a differential operator. Differential is representing the transformations in space and time, and then the fabric of space-time. So what does that do for you? Well, it gives you something, and I've talked about these things before. This is a fully relativistic wave function from a photon in absolute relativity. Doesn't look very familiar, except from when I've talked about it before. But absolute relativity means the exponent of z needs to contain alpha 3, the unit vector in z, and the exponent of t needs to contain alpha 0. These things, this is not a scalar phase, it's actually two phases. And what this object does, it gives you exactly an electromagnetic wave if you do the maths and decompose these things. But what the transformations do is the transformation, if I sit still in space and look at time, I'll see a rotation. If I could, which you can't of course, but if you could move through, move along the photon, what you see is you see it changing from E to B to E around a flying corkscrew along a spiral. So the rotations are different. The rotation in time is a rotation. It's a thing which actually rotates. The rotation in space is from EX to BY to minus EX to minus BY and so on. It's a transformation. It's a different kind of rotation. But they have to be in phase, because otherwise one doesn't have an object which is constrained. And in order to make them into a wave at all, you need to multiply them by an angular momentum, by a quantized angular momentum. And this is where quantum comes in. Why does it have to be a quantized angular momentum? Because this represents something which goes completely round and comes back to where it started. It's a single wavelength. So you go round 2 pi in a single wavelength. This is what a quantum is. It's a continuity condition. That continuity condition, that's what a quantum condition is. This is where quantum comes in. It doesn't come in from somebody saying, oh, no, you're just going to put in commutators the same as a time derivative. They're not the same. They're cause and effect. As Lou was saying, you can replace one with the other in describing the dynamics, but it is one that it is the commutator that causes a change in time. So that equals doesn't mean it's the same as, it means causes or leads to in those cases. Anyway, this is pretty complex. It's some nasty maths again, so let's just go past it. And think about photons. And photons, one's talking about something that contracts, reduces the entire universe to a point from the Lorentz contraction. Again, I won't spend too much time on that. I've talked about this before. And something that James was talking about as well, the linearity of energy and linearity of wave function, square root energy and energy, is actually the transformations of relativity. That's what anyway, we showed that as well, so I've shown that before. Let's get on to chemistry. I've said there are 4 spaces. What are those 4 spaces? Well, three spaces. 4 3 spaces, 3 space of space, 3 space of electric field, 3 space of magnetic field, and the 3 space of spin. And it's spin which is new, you're thinking. The rest are just the same as they've always been, as you would hope and expect. So I'll run through these quite quickly. This is just frequency space. It's based frequency space. So what it's saying is that if you increase the energy, you're going to increase the frequency. Those two are linked to one another of the whole system. That's the base space, which is really an inverse space and an inverse time. Then you've got electric field space, and guess what? That looks like you've always seen electric field space, because that's what electric fields do, and they always did since 1870. So they're completely conventional, as you would expect. The only thing I want to say about this is that that 3D space of electric field space is the 3D space of crystal structure. The 3D-ness of electric structure, of the table I'm sitting next to, is the 3D of the electric interactions between those things. And that's why the table is 3D. And that's why I'm not sitting at a 4D table, because the table isn't made of space-time. It's made of electric field interactions, and they're three-dimensional. So these three spaces are essential. Now, I've been hitting this table, and the thing that really stopped me going through it wasn't the three space of electric field, it was the three space of spin through the exclusion principle. But they're all related because they're all connected to one another, and they're all three spaces, and they have to be. Look at the universe, it's three-dimensional. You look at it. It's three-dimensional. It's three-dimensional for that reason, but it's not. It's really four three-dimensional spaces in terms of the combinatorics of the differentials of the dynamics of space by time. D-space by time, d-space by time by d-space, d-space by time, that's a spin. So you're talking about d-space by time, that's momentum, and you're talking about how that changes in space, that's a circulating momentum, that's an angular momentum. So these things are described by differential quantities, but have the properties that are intrinsic to those differential properties. Magnetic field space, once again, is completely conventional. These are just, there's some more in here, but I won't dwell on it. Spin, this is the interesting one, spin space. Now, the spin of spin space isn't something going round and round in circles. It's a spin field. So everywhere is rotating. Every little bit of space-time that's defined by this differential, it's intensive. It's defined at every point. If I have a spin field which has some boundary and I integrate over that, the integral will be zero everywhere within the boundary. Of course, for everything that's going like this, there's another one next to it which is doing the same thing, and hence cancelling it. So all that spin then gets pushed out to the edge, but as usual with these integrals, one still has the same spin. It just now appears as something which is spinning around the outside, but it isn't spinning around the outside; it's spinning everywhere. But these spin spaces, this spin space is a 3D space as well, so I can orient things in this spin space and look at how they connect. Now, the way this is normally done in E-psi in Schrodinger stuff is you put these things in things like spin-orbit couplings. And talking to the chemist, Brian's a chemist who's worked on these spectroscopists, worked on this thing all his life. He's saying that it used to be the case that people would compete with one another on how many terms they get into the Hamiltonian. And you'd have 50 of these terms. You'd have spin-orbit coupling, spin-spin coupling, nuclear spin connected to spin. You'd have momentum terms, you'd have relativistic correction terms. How many can you get in? So this is a spastic hamburger of a theory by the time. And you're thinking all the time in terms of the effect on energy, in terms of a Hamiltonian. Not good enough. Because spin introduces coherences that are not just energy coherences. The spin coherence is the thing has gone round in a complete circle. That's your quantization. And if you try and deviate just a little bit from that, from your pure note, you're going to get a dissonance. You're going to get something which doesn't match. It's no longer quantized. These things are hard-edged. It's not inverse square, it's not inverse cubed. You are stuck exactly on your quantization. There might be another quantization nearby, a harmony, where you might have a 1/3 or a 2/3 difference, where you can have something which sounds nice in music, but also feels nice to the wave function that you're talking about here, in terms of it coming back and having a harmony. This is how de Broglie derived lambda is h over p in the first place in the simple case. But here it is appearing in where it needs to go, in the spin quantization part of what's happening here.
John, do you think you could start wrapping up?
I could, but I haven't really done much chemistry yet. So I'll just whiz through some chemistry. That's the most important thing I want to do. So Pauling exclusion principle is just arises. It's really a force. I've talked about that before. Quantum bicycle you've seen before. The other thing that happens that's important in chemistry, and these things are all over the place in chemistry, is a dielectron boson, spin inclusion, is a thing that appears everywhere in chemistry. You get a couple of electrons, and this is remarkable, in the helium S shell. Those electrons are sitting precisely on top of one another. They're both negative. They should repel. They don't. They just sit there with no energy change. Why? Well, the reason is that the electric field is coherent, but the magnetic field is also coherent, but it's destructively interfering. Those two precisely cancel one another. So the energy of the electrons sitting on top of one another is precisely the same as the energy of the electrons sitting far apart. This is what we normally call a Cooper pair. This is a dielectron. That dielectron is a new state of matter. Two electrons spin into woven. And these things they're a vortex. They exist hell with energy. These things are interlinked spins. They're vortices which are interlinked. They can have masses. They can be unbound, and they are unbound. The Tate experiment in niobium, trying to measure the mass of Cooper pairs, looking to see whether they were bound or not. They should be slightly less massive, right, than two electrons. But they're more massive. They're not just a bit more massive. They're 10 times more massive than they should be less massive. So there's the reference to that. These things are coherent states. They stick together, but they are not bound by just merely energy. And you should know that too, because in superconductors, high-temperature superconductors, the theory doesn't work for high-temperature superconductors. They shouldn't superconduct, but they do. Experiment rules. So that's a summary of the coherences and what they do. You have coherences that are based on energy, but also ones that are based on spin. And the spin ones are hard-edged. You get into that thing, they persist. So if you consider a spin state in oxygen, for example, in the atmosphere, you'll find that it persists, that it doesn't get thermalized very easily. Now, the normal way you look at these things is you look at these things in terms of spherical harmonics, in terms of the maths. So, but wait a minute, let's just go back to the spherical harmonics. Okay, but the spherical harmonics don't work in chemistry because they work for one electron atoms. What's the use of that? If you're doing chemistry, you've always got at least two atoms, right? Or you've got an atom which has got more than one electron, hey? So if we start looking at the chemistry of those things, the spaces are coupled. All these spaces are coupled up to even to odd, backwards and forwards. And what you end up with is, for real objects in chemistry, they don't follow the nice Cartesian or spherical stuff. Carbon's tetrahedral. The thing gets bent by reality out of shape. And you end up with something which is hybrid. These chemist guys, they keep doing hybridizations. They say, okay, yeah, all right, well, the one-dimensional thing doesn't fit, and the two-dimensional state doesn't fit. These are orthogonal states in Hilbert space, beloved of physicists. So what should we do? We'll hybridize them. We'll just add them together. So what we get now is we get something which kind of goes up and then comes down a little bit because we just added them together. So it's hybridizations all over the place. And do you know why the guys do it? They don't do it. They do it just because it agrees with experiment. So, and you get out of the quantum stuff so quickly in chemistry, and yet you kind of try and use it a little bit. But the reasons for that is the coherence is a different coherence than just the quantum in a box coherence. It's a spin coherence that you're talking about, and that's what you have to think about. So that's what we've been doing, Arnie and I. And here's some beautiful pictures that Arnie's made of different possibilities: platonic solids, spherically symmetric orbits, left to right, spherical, tetrahedral, octahedral, cubic, cube octahedral. An example of that, samarium, iron's cubic, sulfur's octahedral, and cobalt is a couple of pyramids inverted through one another. But the interesting thing is when you start not looking at even more interesting is when you start looking at molecules. So the oxygen molecule is dead interesting. When you take a dioxygen molecule with two oxygens, you introduce an axis, which you could call Z-axis if you wanted. You introduce an axis. This thing's paramagnetic. Oxygen is ridiculously paramagnetic. Why? Because it's a spin coupling running through that axis. And the ground state of oxygen is not a singlet, it's a triplet. It has L equals 1. You have a spin coherence which goes around and comes back in these systems. So, and if you go to crystals, they're coherent harmonic crystals. And that's me at the conclusions. There's a new quantum mechanics which you can use for engineering. It extends Maxwell, Dirac, and underpins QED. It allows new thinking in areas you couldn't think about because you have this possibility of thinking in these new spaces. Therefore, 1D spaces confine, they act as bookends to these 3D spaces. Stuff bounces around in this, but it's stuck by these ends. It's reflected at these ends. The simple mass that one usually uses for this stuff just gets bent by reality in atoms, molecules, and crystals. And what we're doing here, is we're implementing particle physics to chemistry. The next step, of course, is solid state physics. then materials, devices, and we're on to all of this. And that's the end of the talk. Thank you very much for your patience in lots of maths. And I've got 8 minutes left for questions. So I turn things over to everybody and I'll stop sharing. Or can you stop me sharing?
I think you can stop sharing. Yes, thank you so much. And yeah, I think we can go back to the gallery view for me. Okay, Lou. Yes.
John, how does the Aharonov-Bohm effect look from the point of view of your theory?
The Aharonov-Bohm effect. Aharonov-Bohm is part of this stuff, so it looks as it should. I have one of my papers has got Aharonov-Bohm in it, and it's exactly that kind of thing that you need. You have a phase coherence that has to do with the part of it that's acting through the through the vector potential. It's not an imaginary. People used to think that the vector potential was just a fiction that one could add any gauge to. You can't. It's fixed by the other gauge, so it's a physical thing. And really, if you look back at Maxwell as well, he had it exactly right. The relationship between the vector potential and the current is the same relation between the magnetic field and the magnetic between H and B in magnetic field, between the magnetic field and the magnetic flux, and it's the same relation as that between E and D. So this thing is really a current. We're talking about something. The product is never. It's really these things are properly. It's really AJ one should be considering. So if you look in the more advanced literature on these things, Anderson and Arthurs is a good one. A lovely paper by Anderson and Arthurs, where they're talking about AJ as being something which is a proper thing. They're also talking about the need for another gauge, and they're right. They were right, although not thinking in terms of this mathematics. But the vector potential here is, you could think of it as being a mass current. It's like a mass current. It's a mass flow, but it's a constrained mass flow. It's in a box because before it gets very far, something's turned it around. It's back to where it started from with 2 pi or 4 pi or something which brings it back to some coherence, some resonance, coherence is the best word because coherence both coheres as in holding something together and it coheres as in being a multiple of 2 pi. And those conditions exist at the level of the vector potential too. It's a physical thing.
It's been pointed out that the original experiments for Aharonov-Bohm are based on the magnetic field, magnetic potential, and that no one, according to my reading, no one has managed to do it for the electric field, which would be a time energy relationship. I wonder if you know about that, or whether you have a proposal for detecting it for the electric.
Well, you get phase changes with the electric field as well. The electric field will modify the phase of a photon, and so will the magnetic field. In principle, the question is you have a good proposal for an experiment? Much harder because one's talking about things which are magnetic fields. You can get quite big magnetic fields which have huge energy densities.
Yeah.
To do that with electric fields is a lot more difficult in the lab.
Right. Can I point out that we have time for a couple of questions? First Anton and then Michael, please.
Okay.
Thank you.
Thank you, John.
Just 2 questions. The first one is just a yes/no, and then I'll follow with the second question. Is your theory set in relativity?
Is it? Pardon me?
Is your theory set in relativity?
It's it's not set so much as being set in space-time.
Well, space-time is special relativity, isn't it?
No, special relativity is a derivative of space-time. Special relativity is much simpler than space-time. So it's not cause and effect.
Well, let's put it this way: does your theory contradict relativity? Because, in my opinion, it does.
No, why is that, Anton?
Well, it's in slide 11. Slide 11, you show a photon, which is basically which I can look at as a propeller, and special relativity comes from Einstein's thought experiment of surfing down the wave, and because the wave is now standing still, which is in the effect of the red shift. Now, if I'm sitting on an aeroplane wing, with a propeller turning, that frequency never changes. So you cannot, with your theory, you cannot have a red or a blue shift.
No, that's nonsense. That theory has
nonsense. On what basis would that rotation change? Because you're moving next to it.
In that equation, there's a number r. That number is the rate of rotation. You can slide it from 0 to infinity for the same photon, depending which frame you are. The angular momentum remains the same. That wave function is fully relativistic. It's the first fully relativistic photon.
But why should it change?
Well, it changes. Photons do change in a gravitational field, or if you move towards them, it's called a Doppler shift.
Yeah, well, Doppler shift, but basically, if I'm sitting on an aeroplane wing, that propeller never changes.
No, you have to unask the question, because if you're sitting on a photon, both the emitter and the absorber are at the same point in space-time.
So anyway, basically that was my point.
Your airplane wing's infinitesimally thin.
Let's go to the next. Other people want to ask questions.
Okay, Anton.
Yes, Michael.
Good question, but no. Yes,
Okay,
Michael.
Michael.
On the
Thank you, Anton.
future evolution of your work, as you know, there's great hopes that fission will supply energy, and also the piece which is really difficult is to do with plasma. Does your work have relevance to that sort of space?
Well, it does, but you can do far better than that. One can do far, far better than that. I think there's an energy source in here which is 10 times more efficient than fusion, and which is fairly straightforward to generate. So, but that's something I don't want to talk about over a public. So I think yes, it does for fusion, and in fact, I've been in touch with the people in Sapphire, partly to warn them that they're sitting on something very dangerous. They're sitting with an experiment which is producing fusion, nuclear fusion. They are sitting in a container a few meters away from that object. There are some very nasty possibilities that the stuff that they're generating can do to them, like Madame Curie managed to irradiate herself before she understood properly what was happening in those systems. Yes, it does relate very strongly to fusion, and one should also be able to modify the fusion through spin. So one should be able to put a spin field into something and force the thing into having a different rate of fusing. So yes, it does have to do with fusion, but I think we can do at least 10 times better than fusion, and I don't think we need tokamaks.
Thanks very much.
Okay, thank you. I think we can continue this discussion after Mike's talk. There will be sort of forum completely open. So thank you very much, John. And Michael, over to you.
Recording stopped.